Good afternoon, ladies and gentlemen, and thank you for having me here again. It's kind of a hard act to follow Eleanor and Ange, but I'll try and do my best to keep you technically entertained. My talk is about ARM shellcode. This talk is inspired by efforts of many legends in the past. Notably, this was my first inspiration came from Spoonham and Scape when they were still doing the Metasploit 2.0 framework, and they presented a talk at Black Hat, I think 2005 or 2006, about what kind of tricks do you do after EIP control, and they dived into a lot of variety of different shellcode. Now, the x86 world is full of mature shellcode. We all have interpreters and stage shellcodes and whatever have you. The ARM world doesn't. So I started writing things up. These are scribbles from my notes. Oops, this is not my usual laser pointer. Right. So I have a few tricks to present. These are classified as tricks at best. And the tricks have been inspired by the likes of Ange, who walked off the stage a few minutes ago, and Travis Goodspeed for POC or GTFO. And part of my trick involves shellcode polyglots. I too am a big fan of polyglots, and let me take you on this journey. So my name is Saumil Shah. Quick background, I'll give you a very brief background about ARM shellcode, just to kind of get you a little familiar with the three-letter acronyms that are popping up on the screen. And then we're going to talk about two things. I initially started talking about three things, but the problem of cache coherency in ARM systems has been solved rather easily. I had a very complicated technique, so I'm not going to present that. But I'm going to focus on two techniques. One is how do we get around space limitation in shellcode. One of the things I like to do for fun is write exploits, and you're always limited by some space crunches in a few critical exploits. So I put together an ARM egg hunter. And the second trick that I'm going to present is ARM quantum leap shellcode, which involves polyglot instructions. And then, of course, we'll have demos, and I'm hoping that the demos work so that I don't look like a complete fool in front of you. Here we go. Very quick introduction to ARM shellcoding. I'm not going to talk about instructions and such, but typically, whenever you find ARM shellcode in the wild, you have two parts to the shellcode. I mean, ARM, as you know, has fixed width instructions. So every instruction's opcode and operands are 4 bytes long, which to the shellcode writer is a blessing and a curse. The blessing is that the shellcode stays compact. The curse is that you cannot avoid bad characters, like null bytes will sneak in and ugly things will sneak in. So one of the things that ARM shellcoders do is always implement something like an ARM to thumb switch. What you see in the blue is a little snippet of ARM code, which very quickly performs a branch to an odd-numbered address, flipping the processor into thumb mode. Now, ARM, as you know, is one of those weird processors which has two instruction sets simultaneously on it. You have the 4-byte ARM instructions, and then a thumb is smaller than an ARM. Well, it's supposed to be half the size of the ARM, but that'd be very weird. But a thumb instruction is 2 bytes, and it makes the shellcode not only more compact, but gets rid of a lot of bad characters. So shellcoders prefer this technique. They will switch to thumb mode, and then the rest of the shellcode in green goes on in thumb. So if you kind of disassemble it, it looks somewhat like this. You have the 4-byte blue code that switches to the 2-byte aligned green code, and then whatever literal pools you may have. This is typically how ARM shellcode works. Now, I'm going to get very quickly to the first problem. That is, how do we navigate through shellcode, which is limited to very tight spaces? Now, I'm taking a Stack Overflow as an example in this case. You may have a local buffer. You may have a local variable somewhere in the stack. Now, we may have constraints in the size of the payload. For example, what if by increasing your payload, you're going to accidentally overwrite a local variable? This will cause a seg fault. You go past the end of the stack. This will cause a seg fault. and sometimes these will create problems. This is not an old problem. This is, this is not a new problem. This is old. This has been solved before. There's many solutions. And one of the popular solutions is the egg hunter. Now, the egg hunter has been invented many years ago. There's nothing new here. To give you a very quick theory about how the ARM egg how egg hunter works, you kind of load the real shellcode anywhere you like in the memory, where there's space. But you prefix the shellcode with two markers, two eggs, two 4-byte values concatenated successively with one another. And then the egg hunter code searches the memory page after page to see if these two markers appear in succession. If they do, then they know that, hey, the shell is here, let's jump to it, and off you go. Now, the whole process of scanning memory non-destructively, how do you go through virtual memory space and say, is this page here, is this page here, is this page here? What if the page is not here? If you're in user land, you'll cause a seg fault. So you got to have the kernel do this for you, and this happens by using some syscall, which you really don't need. But the moment you have a syscall which takes in a memory address as one of the arguments, you run the syscall. If the syscall comes back as failure, then it says, okay, the memory access was not there. That means the page doesn't exist, and you go on. This technique was what was documented by Spoonem and Scape to safely determine whether a memory page exists or not. Once you find it, great, you transfer the control. So nothing new here. Let me give you a recap of what happens in the present day and age if you use an egg hunter, and specifically an ARM egg hunter. You may choose to load your shellcode up anywhere you like. For example, here I've loaded in the heap. And you notice that it has been prefixed by two markers of arbitrary choice. I've called it hack here, but my production shellcode always uses ABBA because I like ABBA very much. Right. And then you have your Stack Overflow, the usual stuff. You have your ROP chain. But now you can't place the whole shellcode there, so you place a little stub. The egg hunter, important step. Before the ROP chain is very necessary. I kind of forgot that point, because today you have something called data execution prevention, which makes the memory non-executable. If you really want to use it, then you have to have the ROP chain to apply mprotect, make the memory executable again. And then once your stack is executable, you can then jump to your shellcode. Your shellcode will execute. And then the egg hunter goes through scanning page after page until it finds the pattern. It finds both of these eggs. And then it says, okay, shellcode's been confirmed. Now, let's jump here. What's going to happen? Utter failure. This will not work simply because the memory at the heap is not executable yet. So data execution prevention, of course it has been solved by this ROP chain over here, but using the ROP chain, you only apply mprotect to certain region, typically in the same vicinity. Sure, you can build a custom ROP chain to apply mprotect to different regions and then do it, but like I say, a good shellcode must be delivered in style. So the shellcode should do all the style work by itself, and that's what I did. I wrote the ARM mprotect egg hunter, which is as best classified as a trick. So without much further ado, let me show you what the ARM mprotect egg hunter does. There's very minor modifications in the shellcode. Essentially, you want to instead of using a test syscall, you want to use mprotect as the page checking syscall itself, which means that the first time you get control of shellcode, your stack memory is RWX. But now as you're keeping on going, searching through the memory pages, the syscall that you're using to test the memory is mprotect. And as you keep searching through the pages, you're marking them RWX through and through, which means by the time you get to your heap, the heap will be painted executable. We have our eggs in place. boom, you jump, and off you go. So this is the mprotect egg hunter that I want to share with you, and I'll show you, as always, I'll show you a demo of how it's done. And then we'll go to the second part, that is the polyglot shellcode. Right. Demo time. I'm hoping you can read the text all the way at the back. Is it good, or do I need to increase the fonts? All good? Very good. Thank you. Right. Now, I'm going to show you two pieces of code. There is a victim code. Right, here is a classic Stack Overflow bug. The shellcode is a series of ARM breakpoint instructions, which I'm going to malloc and load it into the heap. And of course, I'm going to prefix it with these two eggs. And then down here, you have your classic buffer overflow, the dreaded string copy, which keeps us employed and in business for more than 30 years. Now, right. Okay, sorry, I have to refer to my notes a little bit. Let me show you the code. So here I have the egg hunter code. I'm not going to show the classic egg hunter because that doesn't make sense anyway. Let me straight away go and show you this egg hunter code. By the way, all the shell code is already up on GitHub. You can feel free to steal it, modify it. If you modify it, please let me know because I love new tricks. The core of the egg hunter loop is over here. The syscall that I'm using to test the pages is mprotect, which is hex 7 delta. And I increment the pointer by hex 1000 bytes at a time. And every time I apply the syscall to invoke mprotect, I am also marking the memory protection as RWX. So if the page exists, it becomes executable. If it doesn't, if it's like no memory, then keep on going. And once you find a valid page, then you check for the presence of the two eggs. If the eggs exist, then over here, you simply jump to the shellcode. I'm not going to go into the details of the assembly, but rather let's see this using a demo. I have the script to do the shellcode. So here's your egg hunter code. This is going to search for the pattern hack loaded anywhere in the process memory. Down below, you see the ROP chain. This whole stuff is the ROP chain to apply the first mprotect to get the stack executable and the egg hunter code running. And let's now see how it goes. Got this, and while I'm doing it, let me also get the final code. Got it. Okay, so first let me show you the code running normally. I'm going to crash the whole program with the classic Stack Overflow. There we go, good enough. You should get a segmentation fault. You see the program counter in your control. The stack memory is also overwritten. You stick the egg hunter over here at the stack, and then let's see how it goes. If I look at the memory permissions, currently data execution prevention is on, and the stack is not executable. However, I also have the shellcode that is already present loaded up in the heap. So here's my heap memory at 11,000 hex, and I'm going to search the heap memory for the string hack. I find this string at two locations. So if I now dump the memory at the first location I find, here it is. This is the original shellcode. It's hack, and then all this stuff that you see are the breakpoints. The demo I'm going to give you is, the first demo is we're going to successfully reach the breakpoint, having seen the mprotect egg hunter apply RWX to all the memory pages. So first demo, and then the second one we'll do with the real shellcode to prove that the egg hunter works. Okay. I'm going to do a run ROP demo. So here we go. The egg hunters effectively, I mean, this has crashed. It has crashed at program count of 48, 48, 48, 48, and mprotect has happened. So if I look at the process memory layout, you can see that the stack is now executable. The egg hunter code is where my stack pointer points to. All this stuff is the egg hunter code. If this code runs, then it's going to scan the heap, and then it's going to land me into the breakpoints. So I'm going to run the stuff again, this time without crashing at 48, 48, 48, 48, and effectively we'll reach the breakpoints. So now I'm going to run it with the final payload without crashing, which means the first mprotect goes through, the egg hunter goes through, mprotects everything in the heap, and sure enough, now you see your program counter has already reached the breakpoints in the heap. This memory address that you see here, 11,010, this is the address after the hack. The string is over here. This is the string at 11,008. This is 11,000 hex 10. That's where your program counter is. Program counter is now in the heap. And if I look at the virtual memory map, you can now see that not only is the stack mprotected, but the egg hunter went and applied this all over the process binary until it found the payload. And now the dep issue is not a problem anymore. The shellcode itself is self-contained to bypass the remainder non-executable memory pages and jump to a valid memory page. So that was just a demo with the breakpoints, and of course, no demo is complete without the some shells actually popping up. So let me get there's this one called egg victim, and this is real shellcode. This launches you bin shell. So I'm going to run egg victim. The breakpoint, I'm sorry, and smell. Victim one. And running the final code. Now when you do it, boom, you're dropped into a shell. Code executes, everything is great, and sure enough, commands are running, and then you kind of crash. Right. So that was the first demo. I will now go on to the polyglot shellcode, which I'm sure is what you're really waiting for. Okay. Right. So for the polyglot shellcode, I want to set some context over here. We go back to the classic ARM shellcode diagram. The first part in the shellcode anatomy is that you're going to switch to thumb mode, and the rest of the shellcode is implemented in thumb mode. We've seen this for reasons that I'm going to mention again. It's compact, avoids bad characters, and other things. Now, whenever you're talking about shellcode, and you're discussing this with a bunch of people in the hallway track at any conference, some bright guy is always going to come up and say, hey, I can signature this. This shellcode is going to be signaturable. I'm going to write some Yara rules, and I'm going to do this IDS thing, which was invented several years ago, and catch you in your act. Now, one of the things that really drives me mad is the word signature. I mean, too long have we done InfoSec by rules, signatures, and updates. It's a very reactive technology, just like the dinosaurs, and they need to die. Anyways, I will not rant about signatures again, but whenever I'm confronted with signatures, it only drives me a little further to come up with something that not only bypasses a particular signature, but entire class of signatures and come up with a different class of doing things. And that's what I did. And the next thing was Travis Goodspeed. He told me, he was actually playing with a good watch at the time, and he was saying that, hey, you know what, your trick will also work on some processors which are thumb only. It's like, I didn't know that there was something called just thumb only processors, but yes, some Cortex M0 processors do not contain the ARM instruction set. They're only thumb mode. So now if you popularly do an overflow on a thumb only processor and your instruction is in ARM mode, you're going to get a SIG-ill and die. So this led me to come up with the whole theory of one shellcode to run them all. The goals of quantum leap shellcode is something like this. You may start in ARM mode. The first thing you want to do is very quickly leap to thumb mode. And then the rest of your shellcode should be in thumb mode, which is usual. But if you started in thumb mode, the same instructions that cause you to switch to thumb mode, in thumb mode should do nothing. They should let you just pass through and stay in thumb. This is the Newton's first law of ARM shellcoding. Code that starts in ARM remains in ARM unless it's acted upon by an external switch, with great apologies to the famous scientist. But the same switch should keep you in thumb if you start in thumb. So this is what the whole stunt is about. Polyglot instructions that do one thing in ARM but do nothing in thumb and not destroy our code. For now, the attack is nice and academic. It's worth publishing in POC or GTFO, but I'm sure there'll be some practical applications to this stunt coming out in the future. So what do we need to build quantum leap shellcode? And this is what I'm going to explain you just a little bit. I'm going to try and keep it as simple without going too much details into the depth of ARM and thumb instruction encoding. If we can create well-designed, or rather well-encoded ARM instructions, you'll get a 4-byte sequence in ARM which does something. But the same sequence, when you break up the 4 bytes into two 2-byte thumbs, the thumb instructions simply pass through non-destructively. To pull this off, we have to leverage a few cool features that the ARM instruction set provides us. And there's no formal theory of doing this, all about polyglots. Polyglots are all about lateral thinking. So one of the things that struck me very interesting studying ARM instructions was that all ARM instructions can be made conditional, predicated instructions. Any instruction can be applied with conditional checking that the instruction triggers only if a condition is met or not. So this becomes very helpful. And then, of course, you need some luck and perseverance and iterations. The name Quantum Leap Shellcode was credited to one of my friends named Dial-Up. This was coined at 44Con a couple of months ago. So now let's see what happens if you transform ARM instructions to thumb rather forcibly. Here we begin with the same ARM to thumb switch. This is the part that we're trying to modify. So this stuff is the ARM code. The green stuff is just placeholder thumb code. If we force the ARM disassembly into thumb view, the instructions that you get for these 8 bytes will be something like this. The first thumb instruction, ASRS, stands for arithmetic shift right with status update. So you're shifting right one register with so many bytes, whatever it is. Fine, that is non-destructive. That's cool. But the second instructions that you get, this is a branch instruction. This branches to an offset. Now, branch instructions are destructive. They take away control from our shellcode and kill us. And the next instruction, the BX instruction, if you split it into an ARM thumb instruction, this becomes like a highly complicated vector floating point thumb2 instruction, which I don't know what the bloody hell it does. And I definitely don't want it as a part of my shellcode because it's going to kill me. It looks too large, and large things kill you. So the whole art of polyglotting this relies upon you wanting to avoid destructive instructions. So no branches, no load store, because you might be loading from memory address that doesn't exist, writing to memory that's not writable, no floating point instructions. The other goal is that this should work on a Raspberry Pi 1 or some dumb IP camera, which is ARM v6 core. So we do not want thumb2 instructions as well, the lowest possible denominator. And of course, we don't want sigil, no illegal instructions. So with this, you got to play around with ARM and thumb decoding, which is what I'm going to show you. A quick primer on ARM and thumb decoding. So we take the 4-byte ARM instruction. We take add R1, PC, 1, which basically adds 1 to your program counter. This is responsible for the thumb switch, part of it. If you want to decode it into individual bit patterns, the decoding bits look like this. You have, and I've colored these regions. Each color has a specific meaning. So you have the first 4 bits are the conditional bits. Then you have the immediate flag, you have the opcode that is in red, you have the status bit in purple, and the last, the least significant 4 bits of the most significant 16 bits, confusing, yes, is the first operand. Then you have the destination, and then you have the second operand. This is how the instruction is encoded. Now we're going to split it into 2 thumb instructions. So the least significant half word comes first. This is the first thumb instruction, and this is going to be the second thumb instruction in succession. Now, the second thumb instruction, this one is controlled, the opcode of this instruction is controlled by largely the conditional flags and partially influenced by this operand 1. This is very tricky to control sometimes. The thumb instruction 1, this opcode is controlled by the operands. And you can change the operands at will, so you can influence this opcode rather easily. This is easier to control. But now, how do we turn this into 2 thumb instructions? Let's see. So the first one translates into the arithmetic shift right that I showed you. This is innocent, this is non-destructive, this is going to be okay. The opcode for ASRS is basically influenced by the destination bits that you see. So essentially, the destination bits tell you that this is R1, 0001 is register 1, and that is responsible for the choice of the opcode ASRS that you see in the thumb mode. So this is okay. We survive this. The next one becomes the branch instruction, and these bits, the opcode for the branch instruction is controlled by the conditionals. And this is disaster. So what we want to now do is we want to avoid this destructive branch. If we want to change this branch opcode, we now need to go back and modify the conditionals in the original ARM instruction. But now we kind of have a problem. If we go back and add conditional execution to the ARM instruction, we are not guaranteed its execution. So how do you turn a conditional execution into unconditional execution, which is guaranteed to execute always, but still retain conditional ability? Well, you choose complementary conditions. So you turn a regular instruction into a set of 2 instructions, each with complementary conditions. So add now becomes add if equals, immediately followed by add if not equals. One of them is going to execute no matter what the conditions are, and you've therefore introduced the conditional flag, but still kept the execution intact. And now with this conditional flag being added in, what you now see is now add becomes add any and add EQ. The most significant 4 bits will change, allowing you to control the operand of the second thumb instruction. Or rather, So now let's see what happens if we do this add any and add EQ. How do the splits to thumb look like? So these are the two complementary ARM conditions, ARM instructions. We split the first one. This is arithmetic shift right, which is great, no problem. The second instruction now becomes another arithmetic shift right, because the add if not equals, this 0001 got copied into the opcode of the second thumb instruction, which we now influence and control very well. So this is two non-destructive instructions. And the second one, similarly, is another shift right, and this is logical shift left. So these two instructions became some bit shift instructions, which are not going to bother us. So as a result, we have no destructive instructions in thumb mode at all. This, in ARM mode, will add 1 to the program counter in register 1. In thumb mode, it is going to do some weird bit shifting, which it doesn't matter, it's going to pass us through. So these two tricks that I showed you, first splitting the ARM into two thumbs, second finding out the regions in the encoding which influence both these opcodes, and third is to turn the regular instruction into a conditional, unconditional instructions, a pair of conditional, unconditional instructions. This lets you control the values of the resulting thumb, and this is the basis of polyglotting thumb instructions with ARM instructions. And now, your code, what we really wanted to do is, if you start in ARM, you want to switch to thumb. If you start in thumb, you want to stay in thumb. So the final optimized quantum leap code, hastily optimized, I say, is like this. Every ARM instruction appears in two pairs. So first you add some value to the program counter. You cannot do a branch to a register because a branch causes destructive thumb instructions. So instead of doing the branch, I push a register onto the stack and pop it back into the program counter. Because I do push and pop, I also have to save the stack pointer because I don't want to screw that up. But by the time you do all this stuff, you will land into thumb mode. If you look at this stuff, it is the same instructions, but forced into thumb mode. These will do some bit shifting and not hurt you. Okay, so I know there's 8 minutes left. I'm going to get to the demo first. Once we do the demo, then we'll do questions and answers. Okay. Give me a little bit. So now let's see how we go about arriving at this. I'll show you the first snippet of code. This is called universal mode 0. I called it universal mode until I came up with quantum leap. So here's your simple code, which is switch to thumb, and then you're in thumb, and then let me disassemble this. I'm going to disassemble this in ARM mode at first. So this is the ARM disassembly. 2 instructions in ARM, the rest in thumb. And now I'm going to force thumb disassembly. If you force thumb disassembly, these 2 highlighted instructions become these ugly instructions that I first showed you. So this is no good. This branch is going to kill us, and this vector floating point is also going to kill us. So iterating this, I came to some different approaches where, let me actually go straight. I'm going to go straight to, let me go to universal mode 2. So I did some work with complementary instructions. So this was my primitive approach. So, okay, instead of doing the add and branch, I did the add 2 times. So this is with carry set, and this is with carry clear. I was playing around with the registers so that I don't get null bytes or any weird bytes in there. So by the end of this, I get R4 pointing to the thumb code with an odd numbered bit, so it will switch to thumb. And then instead of the branch, I use a move command to move the register into the program counter. The problem with this is this works, but it generates thumb2 instructions. I'll show you this stuff. If I do universal mode 2, that's okay. But if I force it into thumb mode, this generates 2 thumb2 instructions. These will not work on an ARM v6 core. These will only work on an ARM v7 core. So while this is acceptable, I want still the lowest common denominator because, like I said, shellcode is all about style, right? So you can't be violating style principles here. So we want to do that. So that led me to the third iteration, which is now Quantum Leap 4. This is the final shellcode, which will switch to thumb if you start in ARM mode. You have the add, you have the move, you save the stack pointer into R4. Then you push R4. We add the program counter to R10. We push it into R10 and pop it into PC. We push the stack pointer as R4 and pop it back into the stack pointer. Now, all the thumb instructions end up being innocent pass-through instructions. To arrive at this simply requires a long loop of trial and error. You tweak a few bits until you get instructions that work on both sides. And so then I have the shellcode at the end to test for it. I'm going to do 2 tests. One is I'm going to start in ARM mode, switch to thumb and get the shell. And then second is I'm going to flip to thumb mode, stay in thumb mode through the polyglot shellcode and then still get the shell. So let's do this. So this is the first test. The test in ARM is simple. You start in ARM mode. This is code 32. This stuff is the assembled bytes of the Quantum Leap code, which should switch you to thumb. And this is the thumb code, which should drop you into a shell. So I'm going to do that. If I just run quantum test ARM, I should get a shell, which means we went from ARM to thumb and boom, you have a shell, everything works. The switch happened. Now comes the tricky part. If you start in thumb mode, then you have to stay in thumb mode without switching back. So this is, I don't have a thumb-only processor for the demo, so I artificially forced a thumb switch. But after the thumb switch, I have the same polyglot code over here, which should keep you in thumb mode and not play any tricks, not crash on you, not do any sigils, and then still drop you into a shell. So here, let me GDB this and show you. Let's set a breakpoint. We'll start it and skip to the first 2 instructions, which will now switch me into thumb mode. So now I'm in thumb mode. At this point, we can assume that we have started on a thumb-only processor. And the rest of these instructions over here, all the stuff that you see, this is the polyglot code, but now running as thumb instructions. If I dump the instructions in ARM, these are the ARM instructions at the program counter right now. And if I dump the same instructions in thumb, the same instructions look like this: add, move, compare, something, something, subtract, all non-destructive. And if I now skip ahead by 16 instructions, skip through all these thumb instructions, we will see that we stay in thumb mode. The flag was thumb to begin with. Sorry, this was thumb to begin with. And after doing the step through, I stay in thumb mode. And now I'm able to run my shellcode. If I do a continue, then boom, I'm dropped to my shell. So that's the demo. It worked. I'm very glad it did. Okay. So yes, to kind of conclude, these are some beginning exploratory tricks in shellcode. There's a lot of work to be done in ARM shellcode. It's definitely not as mature as the x86 world. Hopefully what I've done is going to inspire a few more things, and then we're going to start seeing a swelling of creative ARM shellcode floating around, and maybe make its way into the Metasploit framework to be used like plug and play, click and drop shellcode sometime. I would love that. I would certainly love to not write shellcode by hand anymore and use automatic tools. The other thing is, sure, if you want to write a Yara rule, go Yara this. Good luck. And I can come up with hundreds of different polyglot combinations dynamically generated, which means that I also achieve my personal vendetta against signature-based InfoSec. So with this, I want to conclude. The shellcode's up there. My slides are going to be up on SlideShare as soon as I get off the stage. Play with it, and thank you very much. Questions? Any?
This is the first time I've seen a presentation of yours and there's no questions.
No, that's because I sped through it and I was very dense with the code. Sure. Okay, if you do have any questions, you do go through my GitHub stuff and find me later. I'll be here. We'll all be doing yoga tomorrow at 8 a.m. You're welcome to join us as well. But don't ask me ARM shellcoding stuff during yoga. I might break my back. Right. Well, enjoy Luxembourg. Enjoy Hack.lu. Thank you very much for your time and attention.